Hello, welcome to the last case on decomposing irrational fractions into partial. So the last case is different from all the other three cases in that we will be having P of x divided by D of x. But in this case, we want the degree. I'm sure we all know by now what degree is. Degree of P of x. And let me call this degree of Px. Okay, let me just say the degree of Px must be greater or equal to the degree of D of x. This is what makes this an improper fraction. We all understand an improper fraction is when the degree of P of x is greater or equal to the degree of D of x. Simple examples are maybe for improper rationals, we could have the 3x cubed plus 1 divided by 2x minus 1. You can see that the degree in this case of P of x is greater. The degree is 3. Degree is 3, and degree here, the degree here is equal to 1. The degree, we are looking at the highest power of the unknown. So one of the conditions for us to say, not one of the conditions, in fact, we call P of x over D of x improper rational if the degree of the numerator is greater or equal to the degree of the denominator. Now, with that in mind, we can easily see that 2x squared plus 1 over x squared minus 1 is rational because the degree are equal. 3x cubed plus 1 over x squared minus 2 is also rational, improper rational. It's also improper rational because the degree of the numerator is greater. 7x squared plus 2x plus 1 divided by x minus 1 is also improper rational because this degree is less than that of the numerator. Remember all the other three cases, that is the first case when we have distinct linear factors, and the second case where we were talking about repeated roots, repeated factors on the denominator, and finally the third case where we were saying irreducible quadratic. One of the conditions was that the degree of the denominator was supposed to be greater than the degree of the numerator, or the degree of the numerator was supposed to be strictly less than the degree of the denominator. That is what made us use any of those three cases. Now, what I'm going to demonstrate in this particular recording is when do we use this fourth case? So we use this fourth case when we have an improper rational. An improper rational, therefore, occurs if the degree of the numerator is greater or equal to that of the denominator. Now, how do we proceed? I want us to take note from the previous discussions when we were looking at polynomials. We agreed that if we have a polynomial P of x divided by another polynomial D of x such that this P of x is a higher or an equal degree to D of x, the result is Q of x plus the remainder R of x divided by D of x. This result is what we are going to use here to partialize whatever we are given. This is what we shall use to partialize. I think I remember giving a simple example that, for instance, 13 divided by 4 is equal to 3. The remainder is 1 over 4. I remember giving this, and in this case, maybe I can take 13 to be our P of x, 4 to be our D of x, 3 to be the quotient. Now, when you divide, you get 3, but the remainder is 1. You must say over 4. If you simplify, if you remember, this is just over 1. If you simplify what is on your right, you will exactly see that there is equality there. So that is the same aspect when it comes to polynomials. So when you have got an improper polynomial, you divide. Then what remains here, Q of x, you just say it's over 1. You don't need to partialize it because it's not even a rational fraction. It will just be a number. But this one is what you need to deal with after when you have divided. You need to deal with this one. This is what you will need to partialize. So once you partialize this, it means therefore P of x over D of x is equal to Q of x plus this one, which will be also partialized. So the case that you are going to use to partialize the R of x over D of x can either be case 1, depending on the nature of D of x. You may realize that D of x has got distinct roots, in which case then you use case 1. Or you may realize that D of x has repeated roots, in which case you use case 2. Or you may realize that D of x is actually an irreducible quadratic, in which case therefore you use case 3. So perhaps I should give an example to illustrate this aspect, this case 4, the application of case 4. So the simple example will be to decompose into partial fractions, decompose x cubed minus 4x minus 19x minus 35 divided by x squared minus 7x. Now, I think you can easily see that the degree of the numerator is higher than the degree of the denominator. So you cannot use any of the cases that we have discussed so far. You can't use any of the cases. So what do? We have to use Euclidean long division first. And whatever, after dividing, we write our expression in this form, which we can then partialize. So I'm going to divide. So we have x cubed. Oh, sorry, there is I think this should be a squared here on 4x, should be squared, minus 4x squared minus 19x minus 35 divided by x squared minus 7x. So the long division is not a problem. X squared into x cubed, that is x times x squared, that is x cubed, x times minus 7x, that is minus 7x squared. We subtract, this goes, minus 4 minus minus, this is where a lot of us gets lost. Minus 4x minus minus. So that will give us minus 4x plus 7, that is 3x squared. We can bring the minus 19 down, minus 19x. X squared into 3x, that is plus 3. Is that plus 3? Yes, it's plus 3. 3 times x squared, that is 3x squared minus 21x minus. This one goes minus 19 plus 21. So it becomes 2x Is that 2x? Is that 2x? Yes. It's 2x. 2x. Then we need to bring the minus 35 down. That will give us minus 35. So in other words, this is our r of x. That is our r of x. This is our remainder, which is our r of x. This is what we were, this was the divisor. This is our d of x. And this is the original polynomial, which is our p of x. This is the quotient result, which is our q of x. Now, with that in mind, we will rewrite our expression as x cubed minus 4x squared minus 19x minus 35 divided by x squared minus 7x, which is exactly what we wanted to partialize, is equal to x plus 3 plus the remainder 2x minus 35. Divide this by x squared minus 7x. Now, in this form, what it simply means is that this one is over 1. We are not worried with it. You can see that already this expression is now slightly partial, except that the last part, which is this one, is still composite. We need to split it. So that is what we are going to split now. So to split that one, you can see that perhaps we need to factorize first. Can we do the factorization? Possibly not. The numerator cannot be factorized because there is no common factor. Is there a common factor? No. Of course, this one we can factorize. But I think now going forward, what we are going to do is to deal with the last part. So we want to deal with the last part, that is 2x minus 35. So we will say 2x minus 35 divided by x squared minus 7x. This can be written as 2x minus 35. This was not visible, I'm sorry for that. Divided by, then we factor out x minus 7. I'm sure we can see this is a candidate for case 1. Let that be equal to a over x plus b over x minus 7. So we can cross multiply. Actually, it will get 2x minus 35 over x squared minus 7x is equal to a x minus 7, that is case 1 actually, plus b x divided by x squared minus 7x. And we said since these are the same, it implies that 2x minus 35 is equal to a x minus 7 plus bx. So I can let x be equal to 7. Let x be equal to 7 so that I can, maybe I can start with 0. Let x equal to 0. I will have minus 35 equal to minus 7a. Take note that when we put 0 here, b times 0. When we put 0 here, it goes. We remain with minus 35 minus 7a, implying that a is equal to minus 7 into minus 35. That will be 5. A will be equal to 5. And if we have, say, let x be equal to 7, we will have 2 times 7 minus 35 equal to, that will be equal to A7 minus 7 plus 7b, which means that we'll have 14 minus, to check, 14 minus 35, 14 minus 35, that will give me minus 21 is equal to 7b, which implies that b is equal to minus 3. So, which means 2x minus 35 over x squared minus 7x is equal to 5 over x minus 3 over x minus 7. So eventually, now that we've partialized the remaining, so we can write a x cubed minus 4x squared minus 19x minus 35 divided by x squared minus 7x is equal to x plus 3 plus 5 over x minus 3 over x minus 7. This is the complete partialized form of the original given expression. So this is the procedure. When you are given an improper rational, that is improper in the sense that the degree of the numerator is equal to the degree of the denominator, or the degree of the numerator is greater than the degree of the denominator, then you proceed to divide. And when you divide, you make sure we use this result of P of x divided by D of x is equal to Q of x plus the remainder divided by D of x. Now, R of x and D of x is what you need to partialize using either case 1, case 2, case 3, whichever situation. In this case, we've used case 1 because the factors in the denominator were distinct, they were different. So that is how we partialize. Now, just for practice, perhaps I would request you to write down number 2, which is also asking you to partialize. That is 2x squared minus 2x, what is happening here? This is cubed, sorry, I'm sorry for that. 2x cubed minus 5x squared plus x minus 10 divided by x squared minus 4x. You can see that the degree of the numerator is greater, so you need, first of all, perform log division, and then after performing log division, you write it in the form P of x over D of x is equal to Q of x plus R of x divided by D of x, and you deal with R of x divided by D of x. So number 3 is also 2x cubed minus 4x plus 7x squared plus 7. Now, before you divide, make sure you rewrite the numerator so that it reads 2x cubed plus 7x. Maybe let me give a hint here so that rewrite numerator as 2x cubed plus 7x squared minus 4x minus plus 7, then so that you can easily divide. Don't attempt to divide that way, it will confuse you. So thank you very much. I think this marks the end of partial fractions. Practice makes perfect. You need to continue now, practice, go through a lot of examples where you go through a lot of other examples for both case 1, case 2, case 3, case 4. And by the way, I want you to be able to establish which specific case do I use. Not only being able to establish, but you must also be able to say, after establishing that specific case, are you able to know what to do with that particular case? Thank you very much. I hope you will enjoy the recording. Thank you.